Hi all, welcome to the second part of the video lecture on asymptotic analysis. So in the first part of the video we saw in detail what is asymptotic analysis and from step count analysis. When you focus on the dominant terms by ignoring the smaller terms of the function as well as the constant coefficient, you will get this asymptotic running time, right? Asymptotic analysis, step count analysis to asymptotic analysis. This transition is what we seen in the previous video lecture, and we saw that here we focus on the dominant terms, right? And it is typically applicable for very large values of n only. So focus your analysis for large values of n. So that is what does this word asymptotic means. Okay, so focus analysis on larger input size, that is our n. So that is one point, and also focus on dominant term in step count. Okay, so these two things are what is happening here. And for asymptotic analysis we have asymptotic notations, formal mathematical notations, right? Asymptotic notations. Basically we have a phi notation, big O notation, big omega notation, theta notation, small o notation, and small omega notation, right? So these 5 things are what we are having, and the mathematical definition of big O and different examples we explain in the part 1. Okay, so watch all of them and then come to this, then only you will get a idea here, or you can quickly follow this. Big omega notation, as I already told you, big O is going to give you the asymptotic upper bound, right, where big omega is going to give you the asymptotic lower bound. Okay, so just like so you can just it's enough to study one definition, like say if you understand big O clearly, you can follow these things very fastly, because definitions are almost same, only just that condition varies. Hope you remember in big O. So similarly here also you are knowing what is big omega of g of n. It is set of all functions f of n such that there exist positive constants c and n0. All those things we already seen in big O. I am not repeating here. Okay, hope you are already knowing these things, and we want everything to be positive, right? Positive function, positive constant, that is a 0 less than or equal to. Now the condition changes. In big O notation, f of n is less than or equal to some constant c into g of n. Here c into g of n is less than or equal to, so that it is a lower bound now. Okay, so when you write f of n is less than or equal to some constant c into g of n, you can say that g of n is bigger than f of n, right? Or g of n is the upper bound of f of n. So this is how you are denoting it formally. Now when c into g of n is less than or equal to f of n, you can see that this g of n is a lower bound of f of n. So the notation by which you are representing this lower bound is big omega. Okay, you can see that the same f of n is now big omega, lower bound of g of n. So that's all about it. And this criteria you are supposed to meet for all values of input greater than or equal to some value, some cutoff value, say n0. Okay, so your task is to find out the c and n0. Okay, so it's very easy actually. Let me take an example. Say f of n is equal to some 3n minus 5. So what you can do, you just have to find out a value, this. And to find out something, some g of n here. Okay, so it should come here, or you can just write like this is greater than or equal to, both are fine, or you follow this back to some c into some g of n you have to find out. Okay, and you can guess it right now, right? So g of n, can you think of some bigger quantity of n, like n square or something? So definitely it is not going to be less than this, right? So it should be at least n. Okay, so I can try like n itself. So what c you can assume is, so can I assume a value for c like 4 into n less than or equal to 3n minus 5? Because this is going to be greater, right, for larger value of n. Say n is equal to this say 10, simply we can take, you can see here it is 40, here it is 30 minus 5. So this is not going to be true, because what I need is so 3n minus 5 less than or equal to n, some constant I want, and that constant will be something will 3n itself will satisfy, and any value of 3n like minus some epsilon for all epsilon greater than or equal to 0. So this is going to satisfy this. Okay. For example, let me write 3n less than or equal to 3n minus 5. This is true, right? Sorry, this is not going to be true. Why? Because some minus 5 factor is there. So 3n itself is creating problem, because it is equal, you can say like that. Okay, so it should be value less than this. Okay, so what I can tell you is, if I write like some epsilon greater than 0, strictly greater than 0, I think it will work. Say you have to subtract some value. Okay, so if it is, you are taking like a 3n, that minus 5 is going to create a problem, because these two will match and minus 5 will reduce this quantity further. So take like this. Okay, simply let me take say epsilon to be 1, so that it is 2n is less than or equal to 3n minus 5. This is true for sure. So now you have to try with different values. So C you taken like 2. Now what about n0 for all n greater than or equal to n0. So what is the n0 here? You can try with a different value. 1, it is not going to work. You will get a negative value because of this minus 5. 2, it is not going to work. So like that you try with a different value. I think this 5 is going to work. You just verify till value is 4. So that left side I am getting 10, right side I am getting 15 minus 5. So that is that equal condition. So from that point onwards, any value bigger than this 5 is going to satisfy this. Okay. Now if you want, you can go with a very safer side. You small value of C you can choose, so that definitely it is going to be less. Okay. If that is the case, this for all n greater than or equal to 2 itself may be true. Just verify, here it is 1, here it is 1. So 2 will give you an equality condition, and any value greater than this is going to work. Okay, so here, so if you want, you can try with some smaller quantity, like yeah, these two things are trying to say our f of n, that is 3n minus 5, is lower bounded by is big omega of n. Okay, big omega of n, in the sense it's lower bound. So I'm just trying with the different constants, and I mean C for C and n0. Like here I taken C is equal to 2 and n0 is equal to 5. So here it is like C is equal to 0.5 and n0 is equal to some 2. So the thing is that there exists on C and n0, that's all what I need. Okay, so that I'm getting. Okay, so any one of them you just show and prove this formally, but don't take a wrong value. That about it. Now see here itself, what we can say is this 3n minus 5 is hence lower bounded by n. And now what about log n, something like that? Is it lower bounded by log n? Definitely it is smaller quantity, right? So this will be true, but formally if you want to show, you have to see like some, yeah, you have to find out some C into log n, which is less than or equal to this 3n minus 5. Okay, so you can try with some value for this. Let me take say let me try with the 2 log n. Log n by default to the base 2 only, less than or equal to 3n minus 5. Let's try with some values, maybe smaller quantity. So how can you deal with this? You just take n to be some power of 2, so that this will vanish. Like if I am taking like for all n greater than or equal to 32, what is 32? 32 is 2 power 5, so that this quantity, this left side become 2 into 5, right? Because 2 log 2 power 5 to the base 2 will be, so let me use a different color for you to understand. I am experimenting this 32, putting n is equal to 32 or 2 power 5. I will get this side as 2 into 5, just 5, because log 2 power 5 will be 5 log 2 to the base 2, which is 2 to the base 2 is 1, log 2 to the base 2 is 1, so it is just 5 less than or equal to, definitely right, so it's a very bigger quantity. Fine, I'm just trying, maybe it is true for 16 or some smaller quantity also, you can try out, because what I need is just there exists a value for C, so this C I am happy with, and this N0 is okay. Okay, so like that you can experiment. So this is for it, for this. And similarly, any smaller quantity you can try it out, like some say this root 10, because root 10 is n raised to 1 by 2, right? And this is smaller than this will work, and similarly you can try it like what is C and N0, that you can verify yourself. The thing is that any value of n, it is something like this is going to work. Okay, 1 minus epsilon, and where for all epsilon greater than or equal to 0, because n onwards it is going to satisfy, so everything will satisfy this. Okay, so let me take one more example. So this is something we taken and we saw it in detail, right? Now another one can think of is some quadratic term or something else, minus n plus 2. So this is my f of n. Okay, so I just want to know some value less than this, as its lower bound, say it is less than or equal to some constant C into, so minimum this n square will satisfy, right? So now can you tell me a value for C? I think what about trying with 1? You can experiment it, I think it will work. Okay, or 2, so some random, I just need a there exists a C and N0 is what is needed for me. If I am trying with the 2, you know, this is true for, so I already done it in my own way, I am asking you to see it. Okay, check it. So this is greater than or equal to 2, it is going to be true, just verify. In that in this way I can say that so because of this I can say that f of n is equal to big omega of n square. Okay, similarly any smaller quantity also you can say. So the thing is like not only this, so or you can write like this also, 4n square minus n plus 2, this is less than or equal to, means this is greater than or equal to 2n square is holding. So in this case I am getting C is equal to 2 and N0 is equal to 2. Or the same thing will satisfy for some smaller constants also, like 0 0 1 n square. You just experiment. Okay, so this is found to be true for this particular C is like this, and the N0 you just find out. Okay, so what is like that, so this will be true. So the thing is that any value which is smaller than this 4 is going to work at this point. Okay, so like that, you know, this f of n you can either write like this, or you can write like some smaller quantity, like say n log n, or simply log n, or in general something like n raised to 2 minus epsilon is going to work for all epsilon greater than or equal to 0. So this is the whole picture. So like that, for any given function you can write down what is its big omega. Okay, that or what is its lower bound. Now it's time for us to say the third category, third notation, that is theta. Okay, theta notation. So this is typically representing asymptotic tight bound. Okay, so see in this case you can see that this g of n, which is a lower bound, right? This is the asymptotic lower bound for f of n. So here you can see that f of n and g of n are related in such a way that one is a tight bound for other. So typically if you are writing like this, you can say that g of n is a tight bound for f. So it's corresponds to average case analysis. Okay, so it's there is nothing special here, because you know, the basically suppose you are getting f of n is equal to big O of g of n, what you can say that g of n is a upper bound, asymptotic upper bound for this f of n. Okay, now the same g of n you also proved that it is big omega of g of n also. That means it is a asymptotic lower bound for f of n. So from these two you can say that f of n, so maybe from this condition number 1, what you can say, what one can say is to write down something like this f of n should be less than or equal to some constant c into g of n. Okay, so let me denote the constant way, some constant say to match with the definition, some c2, some constant. Okay, similarly to write equation number 2, this c into g of n should be less than or equal to f of n. Okay, so let me take a different constant, say c1, like this. Okay, so I'm in front condition number 1 and 2, I'm getting this. This says that f of n is sitting as a sandwich, something like that, between just some constant c1 into g of n and some another constant c2 into g of n. I'm just varying these constants only. Accordingly, I'm getting a lower bound as well as upper bound as same. If I'm getting like that, I can say that f of n is lower bounded by g of n and it is upper bounded by g of n. So, or it is lower and upper bounded, or it is tight bounded by g of n. Okay. So, that is the whole essence. Now, as usual, there exists positive constant c1, c2 and some n0. Okay. Such that this is true for all values of n greater than or equal to n0. So, that about it. Let me give you one example here. See, yeah, f of n I am taking like something, any example you can take. This is something I worked out, that is why I am taking this. So this is my f of n. So what I have to show is like I want a constant. You know, it is upper bounded by n square and it is lower bounded by n square, that we already know, because that is a tight bound, right? So that now we know that, but formally by using this definition, how one can show it, what you have to do, you have to show like this one, f of n is less than or equal to some constant c1 into n square. Okay, tell me what is the constant. And similarly here it is less than or equal to some another some constant into n square is less than or equal to this f of n. Okay, this is my f of n and this is my g of n. Fine, this is my g of n. Now what I need is a constant value here and another constant value here. So can you tell me what is this constant? So finding the constants is the only effort you are having. You can try with the different values at this side, which are all satisfying this. So you know it is n square, so any value greater than this n square is going to, some 1 2 3 4, those things are going to work here, but I am just taking this 4, okay, randomly. Some I just need their exist, right? Similarly, any value which is less than 1 is going to satisfy here. So let me take something like a 0.5. Now you have to do like you have to try with the n0 value 1 2 3 4 like that, and you can see that here this is going to be true for all n greater than or equal to 6. Okay, something I already experimented, so you can verify this. Okay, so what I got is like till 5 it is violating the condition. Any one of this condition is going to be violated. From 6 onwards both conditions are true. So n0 I got like 6, c1 I got like 0.5. So this is a, when someone is asking you this kind of a question, this is how you have to do. So once you get a value for, so it is something like there exists, okay, there exists some n0, c1, c2 such that this is true. So that is the whole idea. Okay, so that about it. Now let me take one more example for this. Let me say the step count analysis says that an algorithm is taking some step count like 2 power n plus some n raised to 100 plus n square into 3 raised to n. So now it's look like not an easy polynomial, right? There are many terms involved. 2 power n is there, n raised to 100 is there. So you may be wondering what kind of an algorithm it is. So don't think in that way, like some algorithm you can think of, it may be very complex algorithm, say it is made up of say some 3 modules. So first module is taking some 2 power n running time. Maybe it is trying to enumerate all subsets of a given set, something equivalent to that. Okay, so that you know there are 2 power n subsets, so enumerating all of them maybe for some purpose, you for each enumeration assume you could spend some constant amount of time. Actually it is not. So that enumerating all subsets, some 2 power n into constant amount of time you have to spend. Now what about this? This may be like I am trying to print all 100 size subsets. Okay, you know how many 100 size subsets are there. So if you want try to give a meaning to this, enumerating all subsets of a set with the n elements, okay, something like that. And here you can see this is trying to enumerate all 100 element subsets. Okay, so we are not enumerating all subsets, we are just focusing on 100 element subsets, or you are trying to print all 100 length strings that are possible out of some alphabet of size n. It can be anything, okay. So you know, out of n element there are NC 100 possibilities are there. So that many subsets of size 100 are possible, or that many strings are possible with a length 100, okay. And now you know, this is something like order of n raised to 100. Okay, because you know how to find out this n into n minus 1 into n minus 2 into, like that you will do for 100 times, and denominator 1 into 2 into 3 etc. into 100. So denominator is a constant, then n into n minus 1 into n minus 2 into, from that you can see that you are getting a polynomial, n raised to 100 term is coming and all others are smaller than that, okay, something like that. So here this could be enumerating similarly all 3 length strings and doing some processing over each string. And for doing that processing over each string, I am taking n square time, okay. And so it's not like that. So the last one you can say like enumerating all subsets, but it is something like a repetition. With the repetition you are doing, okay. Anyway, I don't want you to tell this much detail. This is step count analysis of some algorithm. Let it do anything, okay. So if you want, it's like yeah, list all 3 length strings. I mean, let me put in bracket repetition of repetition of alphabets allowed, okay, allowed. And also you are doing some kind of processing which is taking some n square time, so something like that. So anyway, conclusion is you have an algorithm, some bigger complex algorithm whose running time you estimated like some 2 power n plus n raised to 100 plus n square into 3 raised to n. Now can you tell me what is the dominating term here? So that is interesting, okay. The first thing is like one term you can observe here is 2 power n term is there, okay, and there is this n raised to 100 is there, and n square into 3 power n is also there, okay. So I can say like this is a typical relation one can observe here, okay. So this understanding is important, but taking examples and reaching, I mean taking substituting different values of n and reaching this kind of a conclusion somewhat difficult actually, because some bigger quantities of n you have to assume. It's possible, fine, but at the same time why it is so, okay. So it is something like you know, first of all this thing you may be convinced, right, this this 2 power n is less than this 3 power n, definitely, right, because so definitely this, when you multiply with n square, this will be bigger. I think there is no confusion at this point, because this is 2 into 2 into 2, this is 3 into 3 into 3, so definitely this will be a bigger quantity, fine. Now what about this n power 100 and 2 power n, or n power 100 and 3 power n, okay. So this is n power 100, this is something I already told you, you are multiplying n 100 times, where when you are writing 2 power n, you can make this n as big as possible, so that the 2 is getting multiplied that much times, or the number is getting doubled that many times, okay. So here, even though it's a very big number, it will stop after multiplication of n, say 100 times. So this 100, this constant is making it smaller. How big is this constant? But here this constant rise to n. So now this is a, let me call it, this is a polynomial term, polynomial in n, okay. So where this is exponential in n, exponential in n, So whenever you have exponential term, you can't even imagine its growth because it's doubling in every iteration, just 2 power n itself. Then you can imagine how bigger will be that 3 power n. Okay, but smaller n values, this may be difficult for you to convince yourself. Take some very big value for n and you will be convinced. Okay, or just remember like that any polynomial term is always lower bounded by any exponential term. How small is those constants, and here how big constant you can make, no issue, and make this as small as possible, still this relation will be true. Okay, something like that. So from all these conclusions, okay, one can say like so you got an idea like this is something that sits as a sandwich, and or the out of all the term, the dominating term is, let me write like dominating term is of course that n square into 3 power n, and I hope you got the reason also. Now if you want to show, so once you understand that, it is easy for you, you can just show some constants and see and explain that the formal definition is also satisfied. Okay, so this is what we are having, less than or equal to, find out some constant c1 into this n square into 3 raised to n. Similarly here also less than or equal to, find out some another constant c2 into n square into 3 raised to n. So like that. So let me, so I just tried with this is 0.25, it is working, you can also verify, and may other value or some strict value also can satisfy. Okay, and this also you see for all n greater than or equal to some n0, find out what is this. Okay, so anyway you got it right. So what is a tight bond? So just focus on the dominating term, that will be the tight bond for sure, and the dominating term will be the upper bond and lower bond. Okay, but upper bonds there are many, lower bonds also there are many, all smaller quantities, like that it is proceeding. So graphically if you are going to represent them, you can see this big O, our requirement is what, this f of n should be smaller asymptotically, I mean it is smaller, I mean it's less than or equal to some constant c into g of n. So that is why c into g of n is growing like this, right, and this is going to happen after some n0. Similarly here the c into g of n should be a smaller or its growth should be smaller, that is what is our requirement, some c into g of n should be less than or equal to f of n. Okay, here and again it's after some n0, here also after some n0 where these three criteria I can correctly tell, like some constant c1 into g of n should be less than or equal to f of n, that again less than or equal to some constant c2 into g of n. This f of n is sitting as a sandwich between these two. Okay, so this is the criteria for so you can graphically I mean if they are asking a question to explain all these notations, you can show the graphical diagram also. See, till this n0 I am not able to predict the behavior, so that is something you show like that, it is getting one is getting larger, then equal, then larger, like that. But from this point onwards I can clearly say c into g of n is larger than f of n, like or its growth is more than f of n, like that. Now about a small o and a small omega, with that let's wind up. So this is something I already given you a hint in the when I discussed that big O and big omega. So this is also going to give you upper bound only, but it is going to give you the loose upper bound. Okay, loose upper bound in the sense so what I can tell, I will take an example. See some similar thing we can take, f of n is equal to 3n plus 5. Okay, and you know that it is upper bounded by n. Okay, so this is big O of n, and at the same time it is big O of n square also, and it is big O of n cube, say big O of n square log n, like that all bigger quantities are going to meet this, and this is a tighter bond, very tighter bond. So that means no value less than this is not going to hold it, right? So it's a tighter bond, or let me say it's a tighter upper bound. Okay, and if you are looking at these terms, they are actually loose upper bonds. They are also upper bonds, but they are loose upper bonds. So this big O you can use to represent both tighter and loose upper bonds. So that is a general notation. When it comes to loose upper bonds, we have a special notation called a small o. So that is more accurate for representing loose upper bonds. So it is something like a small o of so can I say, so my question is 3n plus 5. Okay, so this is my fn. Can I write it like a small o of n. This is wrong. Okay, so small o is only strictly for loose upper bounds. So this is equal to small o of n square. Yes, sorry, small o of, yeah, small o of n square. Yes, it is true. And this is equal to small o of n cube. It is also true. It is equal to small o of n log n. N log n is not going to work because, yeah, n log n will also work because it is order of n only, tighter bond. Okay, fine. All these things are fine. So this is our small o, and this is our big O. Okay, so you have to be, so just write the O big and small like that. Yeah. Now regarding the definition, that you have to be more careful. What makes it special? It is because, you know, how you will be proving that this is big O of n. It is by showing that there exists a constant c, right? For some c, this is going to be true. Okay, some c is enough. Okay, so that is very important. But when it comes to that loose upper bound, so here the tight upper bound is what I was trying to say. I mean loose also for the, this is for the big O. So for big O, this is the definition we are having. So big O is looking for something like this. Okay, now what about a small o? For small o, I want like you know, this is a small o definition, and as well as it is big O. For big O, some c is enough, but for small o, for any c, any constant, this should be true. So that is very important. Okay, and you can see that this is true in the sense, see what you can see, you try with different values like 3n plus 5, you can try with any c value. So what I can tell you is it's some it is n square at this side, so that is making it special. Okay, so if you are putting a value like 1, this will work, but I just want you to verify what is this n0. Okay, so that you can try yourself, but it will be true. Okay, so this you can verify yourself. So similarly, the same thing itself you can try for different values of c. For any c, it will be c0. So how small, even though you may feel like it may not be true, but because of this n square term, how small c you are taking, you just fix some n0 bigger enough such that this will be true. Okay, so that you can try out. Okay, any value you take, so this will be true. So I am fixing bigger values, I mean smaller value, because for bigger value definitely it is going to be true. So that is, you are convinced there. But even though you take any positive value like a very small value like this, you can definitely come up with an n0 such that this inequality is true. Okay, so that makes a difference. So when it comes to small o notation, the requirement is that for any positive constant c greater than 0, there exists a constant. So this is for any. So previously for big O notation, for there exists a constant. So now it is changed into for any. But the remaining things are just same as big O only. There exists a constant n0 such that this condition is true for all n greater than or equal to n. Similarly for smaller notation, yeah, I thought of. So examples are fine, right? You can think of anything like suppose I am giving you some random function, say n cube plus 100 n, say minus 10, like that. So you know, this is actually if you are looking at big O of n cube is correct, right? But can I write it as small o of n cube? Yeah, this is correct and this is wrong. Same thing, you know, when it comes to big O, can I write it like a big O of n square? This is wrong. Small o of n square, that is also wrong, right? So smaller values are not going to meet the criteria. And big O itself, you have many loose upper bounds you can think of, like n cube plus any value, say n raised to 3.5, small o of n raised to 3.5. Fine. Big O of n cube log n, small o of n cube log n. Like that you can think of big O of say 2 power n, small o of 2 power n. So like that all these things are found to be same. I mean both are correct, right? This one and this one. So like that the small o notation. So small o is actually giving you the asymptotic looser upper bounds. Same way small omega. So small omega is going to asymptotic looser lower bounds. For example, So here again that any condition. So f of n, let me say n square plus 100 n, say plus log n, and anything you write in the dominating term is n square, and you know that it is lower bounded by n square, but it is tight, right? So this is the tight lower bound. But now you can think of many loose lower bounds, like it is lower bounded by n also, it is lower bounded by I mean n square, a smaller value, say n log n also. So it is smaller bounded by even log n also. It is lower bounded by say 1 is just a constant. See, all these are looser lower bounds, right? These looser lower bounds you can denote especially using a notation called small omega. So small omega is specifically for looser lower bounds. That means in all those cases, you know, you can write like a small omega of n also, fine. I mean this particular function, I mean you can, this f of n you can write as small omega of n, small omega of n log n, like that. All looser values you can write. But if you are writing like f of n is equal to the same f of n, I mean small omega of n square, this is wrong because I don't want, I just need. So here this is something like less than, but even though you're writing it as equal to, that also fine. The only thing is this looser that is captured by any constant is c. So for me to write like this, what I need is like n square plus 100 n plus log n is less than or equal to say n, and this constant is any constant. This should be true. Okay, so by default for any constant you can see that this is n term, right? So this will be smaller. So you can try with any smaller value or bigger value, this will be true. Okay, so that about it. Okay, some more examples are like say f of n is equal to 2 power n plus 100 n square plus log n, and you know the dominating term is 2 power n, and it is big omega of 2 power n. But can I write it as small omega of 2 power n? This is wrong. This I can't write like this, but it is big omega of 2 power n is correct. And lower bound, further you can think of any lower values of it, like as even n square is correct, even log n is, because we are talking about lower bounds, but these are all looser lower bounds, right? So the best way to express such looser lower bound is by means of this small omega. So you can write like this is equal to small omega of n square and small omega of log n, or any lower values even, okay, less than even small omega of 1.5 raised to n, all are fine. Okay, so like that you can write down. So that about it. So we are concluding all the 5 notation. Like hope you understand. Like big O for asymptotic upper bound, it can be tighter or it can be looser. Big omega for asymptotic lower bound, it can be tighter or looser lower bounds. Theta for the tight bond, so that is only one thing will satisfy that theta. So small o for asymptotic looser upper bounds, not tight. Okay, so exclusively for looser upper bounds. Similarly small omega exclusively for looser lower bounds. Yeah, that about it. Thanks for watching.